This week, we are going to move on from classification models to a little bit of information theory. So we will discuss information, entropy, perplexity, mutual information, and word representation. So the topic is information entropy and word representation. And we will discuss three main items. Okay. The first one is maximum entropy principle. So we will go over information theory, okay, and show that log linear models and the maximum likelihood estimation can actually be the result of a very simple principle called maximum entropy principle. So this is a bit of theory, okay? And then we will talk about some extensions of the basic concept of entropy, and we will show you how these concepts can be used for evaluating language models, etc., or as training objectives. Third, we will discuss mutual information and show how point-wise mutual information can be used to improve word representations. Okay, so first of all, information theory. As computer science background students, you probably all have learned information. For those of you who are not familiar, let me give you a quick introduction, okay? So information, what is information? Information theory was developed in the dawn of computer science. So information is something to help you resolve uncertainty, okay? So before you know whether there's a final exam or not, okay, you have uncertainty about it, right? So if I tell you there is no final exam, I give you some information. So information is that, okay? So how do you quantify information? So because, you know, in natural media, the most convenient way to convey information is a binary state encoding scheme, right? So information is normally measured in terms of how many bits you have. So when I tell you there's no final exam, you know, I resolve ambiguity in 2 choices, right? So I can use 1 bit to encode it, right? 0 means no final exam. 1 means there is final exam. So this is like tossing a coin, right? So, but if you draw a card, okay, from a deck without the jokers, okay, you know there are 4 suits, right? And they're equally many. So before I tell you the suit of the card I draw, you have ambiguity of 4 choices. So if I tell you that I drew a club card, okay, so you resolve the ambiguity from 4 to 1. So how many bits can you use to encode that? It's log 24, right? You use 2 bits. For example, 00 for spade, 01 for heart, 10 for club, and 11 for diamond, all right? So this is like binary encoding, okay? So in a more general case, the information I give you is the original uncertainty minus the remaining uncertainty, okay? So let's still assume that you're drawing a card from a deck of 52, okay? So there are 4 suits, each one containing 13 numbers. So if I tell you I drew a spade ace, you know that there's no ambiguity left, right? So the information I tell you is log 52. Okay, you need to take the ceiling which is a integer, or you don't take the ceiling, which is a real number, okay, minus log2 1, which is log2 52. But if I tell you that the card I draw is a spade card without telling you what is the number, then you know the original ambiguity is 52 choices, right? And now the new ambiguity is 13 choices. It's a spade card, right? So the information I tell you is log2 52 minus log2 13, right? Which is 2 bits. Similarly, if I tell you that the card is an ace, right? So the remaining ambiguity is log2 4, 2 bits, because you have 4 choices, 4 suits. So the information I give you is the original uncertainty minus these 2 bits is log2 13 bits. Okay, log2 52 divided by 4, log2 13 bits, right? So this is all easy to understand. Okay, so I send you a message, I resolve some ambiguity, and I measure this information in a binary number. Right? How many bits is the information? But so what if the choices are of unequal probability? So let's think about drawing balls, tennis balls from a box, okay? So further assume that there are 2 colors. You have red balls, you have green balls, right? So if they have the same numbers, then it's like what we said earlier, right? So I tell you the color, I give you 1 bit of information. What if I have 5 red balls and 3 green balls, right? So at this time, if I tell you I draw a red ball, okay, how much information did I give you? If I tell you that I draw a green ball, how much information did I tell you? Well, you guess I tell you more information if I tell you that this is a green ball, because there are less green balls than red balls, right? So this is intuition, but how do I quantify that? So we can still apply the knowledge we used in the previous slide, right? So originally, you have 8 different choices, right? 8, so 5 red balls, 3 green balls, right? After I tell you that this is a red ball, your ambiguity becomes 3. No, sorry, 5 for red balls. So the information I give you is log2 8 minus log2 5, right? So log2 8 over 5, right? So similarly, if I tell you this is a green ball, then it's a log2 8 over 3, right? So original ambiguity minus the new ambiguity. Without losing generality, so if there are m balls, red balls, and n green balls, then as I show you in this equation, if I tell you that this is a red ball, the information I give you is log2 m plus n over m, okay? So which is log2 1 over the probability of red balls. All right. So in general, so if you have an event of several possible outcomes, right? So for each outcome, if the probability is p, then knowing this outcome contains information of log2 1 over p bits, or minus log2 p bits, all right? So this is information. So information basically measures how much you need to encode one random variable value. Okay, but what if I treat the ball drawing game, okay, as a whole? So that's a random event, right? So this random event has two values. One is red, one is green, right? So if I tell you red, I give you log2 1 over p red information. If I tell you green, I give you log2 1 over p green information, right? What if you treat this whole event, okay, as a single item? So on average, right, if I draw a ball, on average, how much information did I tell you? All right? So you can calculate the mathematical expectation, right? So which is the probability of red ball times the red ball information plus the probability of green ball times the green ball information, right? So this denotes, on average, if I draw a ball, on average, how much information I get, right? This is the mathematical expectation. So earlier, we've measured information about each outcome of a random event, right? So our random event is drawing a ball. There are two outcomes, red or green. We can measure how many bits we need for encoding each outcome. But what if we take the event as a whole, right? So if I draw a ball randomly, how many bits on average do I need to encode this outcome? How do I calculate this? So we need to use the probability of red ball to multiply the number of bits I encode a red ball, right? Plus the probability of the green ball times the number of bits I need to encode the green ball. So in general, if I denote any outcome of an event as R, so this average is a mathematical expectation, okay? So it's the sum of all possible R, PR, the probability of R, times the information in R, namely minus log2 PR, as you see in this equation, okay? So this mathematical expectation is called entropy. So entropy measures some characteristics about a random event or random variable, okay? It's the weighted sum of information over random event outcomes or random variable values. All right. So entropy measures something about our random variable, but what does it measure? Overall, it measures uncertainty. Okay, let's imagine if we have a sure event, an event which we already know the outcome. For example, if you already know there's no final exam this term, okay? So, and I tell you there's no final exam this term, you get no information, right? But if you don't know, you have no information about whether there is a final exam, so I tell you something about it, you have the maximum information. All right? So entropy measures this uncertainty. Let me give you another example. So imagine that you're trying to encode, okay, the result of a casino dice, 6 numbers, right? So if I don't know anything about the dice, okay, let's assume that every number is equally likely. Then how do you encode it? All right, you need the ceiling of log2 6, right? Which is 3 bits to encode every outcome. What are they? You can use the binary numbers, right? 001 for 1, 010 for 2, right? 011 for 3 until like 110 for 6, right? Okay, So you need 3 bits. But if you already know something about the dice, you know that 90% of the time you will get a 1, okay? And 2% of the time you'll get 2, 3, 4, 5, or 6, all right? In this case, you no longer need 3 bits to encode this event. Why? Because I can just take 1 bit to encode 1, all right? So maybe I use 0 to encode 1. And then I add a 1 before the encoding of 226. Okay, 2 was originally 0, 1, 0, right? Now you use 1, 0, 1, 0 to encode 2. Okay? Similarly, 3 was originally 0, 1, 1, right? Now you use 1, 0, 1, 1 to encode 3. Then I send you a long string of this message, okay, to tell you the result of a sequence of casino dice casting. Then how do you interpret this sequence of binary numbers? So whenever you see a 0, you know I got a 1, right? And you continue to read the next bit. So if the next bit is 1, you read the next 3 bits, right? And the next 3 bits encodes like the number 2 to 6. So how many bits do I need on average to encode this long sequence of events? You know, that will be 0.9. 90% of the time, you only need 1 bit, right? Plus the other 10% of the time, you need 4 bits, right? So that will be 0.9 plus 0.4, which is equal to 1.3 bits. You only need 1.3 bits to encode a number on average. All right, so which is much smaller than 3. All right, this is the second example I tell you. The more uneven or certain you are about an event, the less information you receive if I tell you something about the event, okay? In addition to these 2 intuitive examples, I can also draw you the entropy value of random events. So this is an example of coin tossing, you know. The x-axis shows you the probability of heads. The y-axis shows you the entropy of this random event, all right? So as you can see, if you're completely certain that there is no head, okay, the entropy is 0. You get no information if I tell you. It must be tail, all right? Similarly, if the probability of head is 1, okay, if you're completely certain it'll be head, and I tell you it's a head, you get no information. The entropy will rise if the probability of head grows from 0 to 0.5, okay, and reach the maximum if the probability is 0.5. All right, so this is entropy. All right, maybe you know it. Okay, now let me tell you a principle in machine learning, which is called the maximum entropy principle. It tells you when you build a model, okay, what do I mean by building a model? I mean, if you already have a probability model and you have the modeling target, okay, it's a random event. Okay, the principle is, okay, you should keep your model probability with the largest entropy, okay, given any constraint or knowledge you have. That knowledge could be the training data, all right? Let me repeat myself. You should not assume any information, okay, beyond your training data when you build your model. What does that involve? That involves both the parameterization and the training, right? So when you have a modeling target, you only know that I'm going to build a model, okay, towards this probability. maybe py given x, okay? You don't know how to parameterize your model yet, and you don't know how to train the parameter values yet. So those are the second and third steps in building a model. But I just tell you a principle, which is you take the training data as knowledge and do not assume anything else than that. That's the safest, right? And this principle is can be traced back to like the 14th century, okay? It's named Occam's razor because there is a famous William of Occam who said that entities should not be multiplied beyond necessity. This means that don't assume anything about something, right? Unless you know about it, all right? So before I tell you there is no final exam, do not assume that there will not be a final exam, all right? That's the safest choice, okay? So how do you apply this principle for building a model is what I want to tell you next, okay? So let's just get our hands wet by building a very, very simple model. So there's no training data. Assume that there's no training data. And we only know the modeling target, okay, is a categorical random variable, which is like casting a dice, right? Or drawing a word, whatever, okay? So you know that the probability of this can be denoted as like PR. Every outcome is R, okay? Further, let us assume that our parameterization is to take the probability of each outcome or each word as a model parameter, okay? So if you draw a word, then you know you have the vocabulary size number of parameters. So this is exactly what we did in week 3, okay? So let's use the maximum entropy principle to train this model. So first of all, I draw you what is the entropy of this a model, all right? So it's the sum of, you know, so minus PR times log 2 PR. And then the maximum entropy principle will result in a training objective, right? So which is to maximize this equation, all right? But there's a constraint. The constraint is that the probabilities will sum up to 1, okay? All right, so we maximize this entropy under the constraint that the probabilities sum up to 1. So this is the last two equations. So how do you find a constrained maximum or a constraint minimum? You all know. Remember in your calculus class, which you had maybe a year ago, right? You can use the Lagrangian multipliers, the Lagrangian equation to solve the problem, right? So the basic idea is to turn a constraint a minimization problem into an unconstrained minimization problem, right? Given that your constraints are like equality constraints, right? All right. Okay, so the training objective, I write it in the first two equations. Okay, to find argmin of this thing given this constraint, and we put the constraint into a part of the objective function. Okay, I use a Lagrangian multiplier lambda, okay, on it, okay, as a factor on it. So you need to minimize this Lagrangian equation, all right? So how do you minimize it? So so you need to take the derivative, okay, with respect to every model parameter, PR, okay. So when you do that, you realize you need to set the partial derivative to 0 to every PR, right? So which means that every probability is equal, right? And they are all equal to 1 over the number of outcomes. Okay, so that's a very simple exercise. What conclusion did I arrive at? So it's obvious, right? The conclusion I arrive at is I mathematically proved to you that a random event with the maximum entropy is a uniform distribution. Okay, if the random variable is a categorical random variable. So this exercise does not give us too much information, but it tells us, okay, how do I derive a model, right? The process of deriving a model. Now, let us derive a more serious model, okay? Let's do it seriously. Now assume that we have training data, okay? And further, let's assume that we're deriving a probability model, probabilistic model, okay? The modeling target is py given x, okay? Without losing generality, let's assume that we're doing classification, text classification. So x is a document and y is a class label, all right? So first of all, how do you define the entropy for a conditional random variable? Okay, so here it is. I tell you, for a conditional random event, so the entropy of y given x is equal to the sum of all possible x and y, p xy, the joint probability, multiplied by negative log 2 py given x. Okay. So this is called conditional entropy. But some of you will come and ask me, why is it not the sum of all x and y, py given x times log 2 1 over py given x? Why is it pxy? I have an explanation, okay? So if you know what x is, if you know what is x, all right, then py given x will be similar to py without condition, right? Because you know the condition. So of course, then you get an entropy equation, which is the sum of py given x times minus log 2 py given x, right? But now you don't know x, right? X can be any input. As a result, you have to find the mathematical expectation over all possible x, right? So it's sum x px times whatever you said earlier, you know? And then if you multiply this px using, you know, distributivity, then you arrive at my equation on top. Right, so this is a conditional entropy. All right. So the first step, okay, our modeling target is py given x. So now we got a set of training data, right? So the training data are capital N training examples, right? Each training example is a pair, x and y, document and class label, right? And further, let us assume that we're building a feature-based model. So what is this feature-based model? So our model makes use of phi xy in making prediction, okay? So this is what we learned in the last 2 weeks. What is phi xy? Phi xy is a vector of f1, f2 until fm. It's a long vector, okay? You all remember these feature instances, right? So the first feature representation we built is a word and the class label combination feature template, right? So maybe F538 will be the number is gold, and the class label is sport, right? It's very long, right? The feature vector is of a size of the vocabulary size times the number of class labels, right? So let us assume that in our model, we have this feature representation phi, and let us not assume anything else about it, okay? All right, then you have a set of training data, and you have this feature representation. Then next, how do we derive a model? You know, how do I derive a model? I can use the maximum entropy principle. I need to maximize this hy given x, okay? Which contains px and py given x. All right, okay, py given x is our model, right? It's what our model calculates. So we need to leave it in the equation. But px, what is px? Px is the probability of any input, okay? We know nothing about it, all right? So we cannot calculate px. How do we solve this problem? We can use p tilde x to approximate px, right? So p tilde x means in my training data, all right? If my training data contains d document class pairs, you know, then every document, I assume there's no duplication in my training data, right? So every training document has a probability 1 over d. All right. Good. So I approximate px, and now the only thing I left is py given x. So our goal is to maximize hy given x, and px is already solved. So this is what we're going to maximize. Okay. All right. So Occam's razor said entities should be not multiplied beyond necessity. Okay. All right. So what is necessary? The necessary thing is we know something about these features in our data, right? So because I didn't tell you how to parameterize the model. I only told you, okay, for every input and output pair, I represent them in a feature vector. That's the only thing I tell you. So I need to translate my knowledge of this training data into something I can calculate using features, okay? Maybe in my model. So I have two things I can calculate about feature. So one thing is the empirical count of a feature, okay? So I can count, okay, in any input-output pair, okay? So what is the feature vector? I can do it, right? This is what I count. On the other hand, I'm telling you for any input and output pair, maybe I can use my model, okay? Maybe I can use my model to calculate, okay, how many times you encounter every feature according to the probability of this input-output pair. So how do I achieve that? Okay. So this is the equation. All right. So, all right. Let me rephrase it, okay? And my apologies. So, I'm not using one input-output pair, okay, as the unit, okay? But I'm using every feature instance as the unit, okay? You know the feature vector contains a lot of feature instances, right? So, but maybe we can look at every feature instance. Let's say the feature instance is IC, the word is gold, the class label is sport, okay? So this is one instance, right? Another instance is that the word is finance, the word is gold, the class label is finance, right? That's another feature instance. Let's look at the feature instances one by one, okay? So I can sort of calculate the expectation of the feature instance over the set of training data. So how do I do that? I can do that by just doing accounting, you know. I go through every training example, right? For every training example, I turn that into a feature vector, right? And the feature vector has the count of this feature instance as one element, right? So every training instance has a feature count in this feature instance, and I average them. Can I average them? So this is this equation, okay? So the sum over all training data, the probability of this training instance, which is 1 over d, I assume there's no duplication, times the feature instance in this data, okay, in this instance, which is how many times, okay, did the word go occur in my document, and whether the document is labeled sports, right? If it is not labeled sports, then the count is 0. If it's labeled sports, then the count is the number of go in this document, right? Okay. So this is the empirical feature, which is just average overall training data. So this is understandable. Then I'm saying you can use the model also to calculate the expectation of the feature. So how do I do it? So I can go over the training instance again, right? I can go over the training instance again. And I use the probability of the training instance, px, which is 1 over d, right? And then I enumerate all possible class labels. Let us assume we do not know the gold class label. We do not know that the document is labeled sports, right? I can assume that it could be sports, finance, politics, and technology, okay? So I enumerate all possible y. Then what I do, for every possible output, okay, I calculate the model probability of the output given the input, py given x, right? And then I count the feature instances in this xy pair, okay? So given this document, okay, I have 5 goals, okay? And I calculate if the model labels it sports, the probability is 0.9. So I use 0.9 times 5, okay? So this is a feature count. But if it is technology, I have a model probability, no matter what it is. But this feature doesn't fire because the feature is go and sports. So I ignore all the other things, right? So for every possible, for every input in my training data, I enumerate possible outputs, I count the feature vector in the outputs, and I use this model probability to calculate the weighted sum. Right? So this is the model expectation of the feature. Now, all my knowledge can be denoted as the expectation of every feature according to our model is the same as the expectation of this feature according to the data. All right? So this is the only knowledge I have about our data set. So this is a constraint. All right? So the second constraint is that for all the class labels, the probability sum up to 1. So let me recap it. Recap. So the modeling target is PYX. That's the model we need to build. We don't have the parameterization, but we have the representation of the input-output pair, okay, which is phi. So our maximum entropy model will maximize H, Py given X, under 2 constraints. The first constraint is knowledge in our data, okay? So which is represented by the expectation of every feature instance according to the model is the same as the count over the data. So this is the first constraint. Second constraint is that the probabilities, they add up to 1. Again, this is a constraint maximization problem, right? So we can do it by using Lagrangian multipliers. Okay, the first equation is the maximum entropy objective under the constraint. The last equation is the Lagrangian equation, where the first constraint is denoted in this, okay? For every feature model expectation minus empirical expectation is 0. The second constraint is for every input in the data set, okay, the sum of the output probability is 1. Okay? 2 constraints and 1 entropy. What is more, the only random variable in this equation is now our model probability. Okay? The only random variable is our model probability. So how do I calculate these, the optimal value? You need to use your calculus knowledge. But this time, the random variable is an equation. It's not a parameter anymore, right? It's an equation, py given x. You don't know what it is, right? I didn't specify it. It's not a number. It's a function, right? How do I change a function to maximize an equation? So it's the same, right? Variational inference. So you can fix every input in the function, calculate the derivative, right? And you got the shape of the function. Due to time constraint, I cannot derive it. But I think using your calculus knowledge, you can all do it offline, okay? The result is something like this. Okay, I don't know my function, but I change my function to optimize the Lagrangian equation, and my function looks like this. So it's e to the power of sum lambda I, where lambda I is the Lagrangian multiplier for the feature constraint for feature I, okay? Sum I, lambda I fi, e to the power of this, divided by, okay, the sum of all possible output y, okay, e to the power of sum lambda I fi. Okay, so this is the conclusion. And you will also get the same conclusion if you do it. But what it is? The first thing you observe that this is a softmax function, right? Can you see that this is a softmax function? It's e to the power of like something about xy divided by all possible y prime, e to the power of something about xy prime. So it's softmax. What is the softmax about? The softmax is about, I'm saying, the softmax p y given x is equal to softmax of sum, all the features, right? Lambda I fi. So what it is? What it is? This is theta dot phi. Why? Because phi is the vector of f1, f2, f3 until f whatever, right? So what is theta? Theta is a vector of all these Lagrangian multipliers, right? Okay, so amazing, right? So I'm just trying to find a maximum entropy model, but I parameterized my model into a log linear model, okay? So that's why a log linear model is a very elegant model. Okay? So because there are many possible activation functions to turn this lambda theta phi from the domain of negative infinity to positive infinity, why do I choose softmax? Because the maximum entropy model told us we need to choose the softmax function. Okay? All right. So, and then this is not the end of it, right? Because I still need to find the value of these Lagrangian multipliers when I find the maximize the value of the entropy function. Read your textbook. It turns out that the process when I find the maximum lambda values is maximum likelihood estimation. Okay? So by using the maximum entropy principle, I fulfilled both step 2, the parameterization, and step 3, the training. Okay? And that's pretty much what I have to end up in the first class. Okay, let's take a small break. Now let's consider some other metrics. So we are going to discuss several information theoretic measures between two distributions of the same random variable. So first, let's look at a measure called KL divergence. So to introduce this, let's first revisit the risk we had learned, okay? So remember last week we said the risk, empirical risk, is the mathematical expectation or the sum of a loss over every data over a training set, okay? So we could write a general equation like it's equal to 1 over n, the loss of theta dot phi di. So if we assume that the data set contains d1, d2, d3 until dn, okay? So further, let us assume that we're building a probability model. So in this case, we might calculate the loss as the difference between our model probability Q of di and some empirical probability P of di. And I have to use P tilde because this P of di is sort of calculated over the empirical data. So how do you define this difference? Okay, a very intuitive definition is to use maybe the difference between the log probabilities, okay? So I say I calculate the loss of any training data by using log 2 P of di minus log 2 Q of di. So what is this P tilde of di then? So let us assume that every training instance, okay, di is not duplicated. So this P tilde of di will be 1 over n, okay? So where n is the number of training instances in a data set. And also note that this 1 over n in the very beginning of this risk function is also P tilde di. So we can generalize this equation into the sum of all possible data instance P tilde times log 2 P tilde minus log 2 Q, okay? And also that is equal to the sum of every instance P times log 2 P over Q. Okay. So this equation is called the KL divergence, okay? But we generalized, right? We generalized from the empirical data set of n instances, okay, into two random variables. Okay, so if we forget about this P tilde, and we say, if a random variable has m, capital M, different values, all right? So the KL divergence between two distributions P and Q will be the sum of all possible outcomes, okay? Ri, right? So P of Ri times log 2 P of Ri divided by Q of Ri. All right, so this is a measure. Or you can find that this is a mathematical expectation as well. The random variable I use is the same between P and Q, okay? And I'm using the probability distribution P to do the mathematical expectation. And the thing I do, okay, the thing I calculate weighted average for is log 2 P divided by Q. Okay, so it's a difference between P and Q. And it's a little bit like an entropy, okay? So the thing you notice is that this divergence measure is not symmetric. So when I use Q as the weighted average, I calculate this KL divergence between Q and P. It'll be difference from the KL divergence of P and Q. Okay. Now, so because P and Q, this KL divergence measures the difference between two probability distributions, it can be used as a loss function. Okay, let's go back from this general form to the form of our data set. Okay, let us again go back to the P tilde case. In this case, so every document, every training instance DI is a random variable value. Okay, so we are calculating the KL between the data set P tilde distribution and the model distribution Q. Okay, so what if I train a model? I train the model Q, okay, to minimize this KL divergence between the data and the model. Hereby, I'm assuming that you already have a parameterization of the model. You already know how to calculate Q, okay, using your model parameters. So by using this training objective, I am minimizing sum, okay, P log 2P minus sum P log 2Q. But the first thing you notice is that the first term is a constant because P is just an empirical count. So it doesn't affect the optimization of my model. So I only need to minimize the second term, which is I minimize the sum of log 2 QD. Okay? I minimize the sum of 1 over n log 2Q. Okay, which is I maximize the sum of 1 over n log 2Q. What is this? This is the log likelihood of my data, right? So the sum of the log probability of every data instance is the maximum likelihood. Okay, so I'm saying that minimizing KL divergence is equal to maximizing log likelihood. All right, okay. So in this week, I mentioned two things, right? So the first thing is by maximizing entropy, I'm maximizing the log likelihood of my data. The second thing is by minimizing KL divergence, I'm also maximizing the log likelihood of my data. Okay, a lot of evidence is that MLE is a very nice training objective, right? But what is this second term? This second term looks like an entropy, okay? But this entropy uses a probability distribution P to average log 2 of Q, okay? What does it intuitively tell us? It tells us, okay, let us use the distribution Q to encode my message, okay? So for every possible outcome of my random event, I use minus log 2Q bits to encode it, all right? However, I'm not calculating the expected number of bits by using Q. But I'm using P, I'm using another probability distribution, okay? So this is called cross entropy. So formally, okay, I use HPQ to denote a cross entropy, which is to use the distribution P, okay, to find the mathematical expectation of minus log 2q. So in the book, in the textbook, you will see that cross entropy is always higher than the entropy itself. Because in information theory, if you use a probability distribution Q, okay, to encode some random variable distributed in Q, you save the maximum number of bits. All right, so this is the first thing. And when P and Q are the same, okay, HPQ is equal to HP, it's the minimum. All right. So the second thing, because HPQ is always larger than HP, this KL divergence is equal to HPQ minus HP. So my second observation is that KL divergence is always greater or equal to 0. Okay? And actually, the range of a KL divergence is 0 to infinity. Okay? All right. And let's come back to the minimization of KL divergence, which is equal to the minimization of cross entropy. Okay? As a result, we can use cross entropy as a loss function. So when I mention cross entropy loss, you know that I'm doing minimization of KL divergence or maximization of log likelihood. Okay? So when I say I train a large language model using cross entropy loss, I mean the same as when I say I train my large language model using maximum likelihood estimation. Okay, it's just that I turn that into a loss function term. Okay, so a final remark. Okay, final remark. You know KL divergence is between 0 and infinity. Do you have a KL do you have an alternative to KL divergence that ranges between 0 and 1? Okay. You know KL divergence is non-symmetric between the two distributions. Do you have a divergence value that is symmetric between two distributions? You can check a distribution called Jensen-Shannon divergence or JS divergence. Okay, but I don't have time to cover that in this lecture. So the next topic I want to go over is model perplexity, okay, and evaluation of language models. Perplexity, it is a different way to represent entropy. It's basically equal to 2 to the power of entropy in this equation. So you can understand perplexity of representing the same thing as entropy, but using a 2 to the power form. Okay. So what does it mean? Okay. You know, entropy is the average number of bits I encode every outcome, right, of a random event. So if I take 2 to the power of that, okay, the intuition is I get the number of choices you essentially have, okay, when the choices are equally likely. Okay, so for a fair dice, okay, the entropy is 1. You use 1 bit to encode the fair dice, right? The perplexity is 2. You have 2 faces, okay, of equal probability. for an unfair dice, the entropy will be smaller than 1, right? And 2 to the entropy will be smaller than 2. So that's the perplexity, okay? So which means the coin will have less than 2 faces, essentially, okay, if they are equally likely. In the extreme case, when you know that the coin is very, very unfair, every time it lands facing up, right? The entropy is 0, as you know, and the perplexity is 1. It is to say, the coin has only one side, right? Because you know the result. Okay, so why is it called perplexity? Because the more choices you have, okay, which are equally likely, the more perplexed you are about this random event, right? So it's very intuitively called perplexity. So this is the first thing. Second thing, we had cross entropy, okay, to measure the difference between two distributions of the same random variable. So what if you take 2 to the power of this cross entropy, okay? This is also a perplexity. The perplexity can measure the difference or variation between two distributions, okay? Now let's turn this general form into a form between a data distribution or relative frequency and a model distribution. You get, okay, the cross entropy, okay, the cross entropy term in the power term. So it's 2 to the power of cross entropy, okay, between the data and the model. This is called model perplexity, okay. It tells you how different is, okay, the model from the data. All right. The larger the value is, the more different the model is from the data. Okay? All right. Can we use that as a training objective? Yes, of course we can, right? When we use this model perplexity as a training objective, we are the same as optimizing the model using cross-entropy loss, right? But we can also use this to evaluate a model. Okay, how do I do that? You know, for evaluating classification models, we can directly use a test set and measure how many test instances are predicted correctly, okay? But for evaluating a language model, we could not do that because we can generate arbitrary sentences that are correct, okay? So there is no gold standard answer when I evaluate a language model. We can just use the model to generate and generate, but there's no gold standard correct answer. So there's no way we can do a one-to-one rule-based comparison here. Okay, so how do I evaluate a language model? We can take a set of human written data, okay, as a test set or as a test corpus. And we run the model over the corpus. The model will give us probabilities over these human written sentences, all right? And then we have an empirical distribution, which is by counting, okay, over the data. And we have a model distribution, okay, which is the model probability over the sentences. Now we can calculate cross entropy, and we can use 2 to the power of this cross entropy to calculate the perplexity. So this is how we evaluate language models. All right. So the less the perplexity, the better the model because it coincides more with the human data. So if I calculate sentence level probabilities, okay, the entropy is on the level of hundreds by n-gram language models. And the perplexity is very perplex. It's like 2 to the power of hundreds, okay? So essentially you are saying in the world there are to do the 100 sentences that are equally likely. And that's a lot, right? So a more sensible way to measure model perplexity is to measure it word by word, okay? So we're assuming that a language model can give a probability to every word, right? And then when we have a test corpus, we can run the language model over the test corpus to calculate the probability of every word, right? And then we can use that to calculate the model perplexity, which is written in this equation, okay? So it's essentially 2 to the power of a sum of model probabilities, okay? Then this perplexity for n-gram language models is smaller, okay? It could be in the level of 100 to 200 for n-gram language models, which means, okay, if I look at the corpus, an n-gram language model will see for every word I have equally likely 200 choices, okay? They are perplexed by 200 choices. For neural language models, this perplexity can be reduced to about 10. So which says the model is perplexed as if when I predict every word, there are 10 equally choices, 10 equally likely choices. For large language models, now this perplexity is even lower, okay? To what? To something close to 1. Okay. So they fit data very well. Now that's all about measures between 2 probability distributions of the same random variable. Okay. We talked about KL divergence, cross entropy, and 2 to the power of cross entropy, which is model perplexity. Okay. And I also mentioned one divergence called the JS divergence, which is a symmetric divergence. All right. The next few minutes I want to spend on calculating the difference between 2 random variables. Okay. This is mutual information. Okay. What is mutual information? Mutual information is the expected number of bits you can save for encoding a random variable when you know a second random variable. Okay. All right. So maybe the first random variable is you don't know whether there is a final exam. Okay. You have some entropy. Okay. Maybe the entropy is 1. It's very high. And then you know that the teacher is Yue Zhang. Okay. Then when you know the teacher is Yue Zhang, then maybe the entropy of having a final exam is smaller. Okay. So because in your experience, Yue Zhang normally doesn't give you any final exam, but examines you on your course project. Okay. So this is about it, okay? So what is the equation? Okay. So formally, mutual information is the difference between the entropy of a random variable y, okay, and the conditional entropy of the random variable y given a random variable x, okay? It is written as this second equation, okay? So which is the entropy of y minus the conditional, the entropy of y minus the conditional random entropy. So, and the third equation is the result. How do I derive it? Okay, I leave it to you to read the textbook. So it's quite simple. The only trick is to turn py equal into the sum of all possible x, pxy. Okay, So this is what? This is marginalization, right? So if you just look at the equation and you replace py with this, and you get the third equation. Okay. All right. So this is mutual information. It's denoted as IXY. And by carefully deriving the equation, you will see that mutual information is symmetric. Okay. So basically, the number of bits you save, okay, for encoding y when you know x is the same as the number of bits you save for encoding x when you know y. Okay. So and also we can draw that conclusion in this figure. Okay. So the red circle is the number of bits you encode x. The green circle is the number of bits you need to encode y, or the entropy. So in between, the yellow part is their mutual information. Okay? So the red circle minus the yellow part is the conditional entropy for x given y. And the green circle minus the yellow part is the conditional entropy of y given x. Okay, so this is their correlation. And if you read more, okay, you will find that the whole thing is the entropy of the joint probability between x and y. Okay? Okay. I will leave it to you, because some of you already learned information theory. But then the mutual information, okay, in its form, is a mathematical expectation. It is an expectation by using the joint event probability. Okay? And what is averaged is log 2 of pxy divided by px py. Okay. So if I take any xy instance out, okay, and only look at log 2 pxy divided by px py, this is called pointwise mutual information. Okay? And mutual information is basically a mathematical expectation over pointwise mutual information. I can draw an analogy. Entropy is the mathematical expectation of information, right? And mutual information is the mathematical expectation of pointwise mutual information. All right. So as a result, this information about one random variable is also called self-information, just to differentiate it with pointwise mutual information. You have an exercise that says mutual information is non-negative. Okay? So if you know a random variable, you can only reduce the uncertainty about another, or do not change the uncertainty. But pointwise mutual information can be negative. Okay. How do we intuitively understand pointwise information? So the numerator is the joint probability, right? So when two, this pointwise mutual information is about random variable values, okay? When two values of two random variables always occur together, or they always co-occur, the joint probability is high, okay? And the denominator is the probability of each one, okay? So it's like, okay, we need to co-occur frequently, okay? And neither of us are frequent. And this means we are highly correlated, okay? The two values of the two random variables are highly correlated, okay? But if both are very frequent, but they don't occur together very frequently, then the pointwise mutual information is negative, okay? Which means they're negatively correlated. Now, how can we make use of the fact? Right. So in NLP, there are a lot of cases, right? Two things, when they occur together, they occur together. And we want to make use of the fact to mine out useful information from data. So let me give you 3 examples. The first is word and sentiment signals. The second are 2 words that are always occur together. And the third is a feature and a class label. Okay, let's look at the first one. You know, sentiment lexicon is a dictionary with words and their sentiment values. What is a sentiment value? So the sentiment value could be maybe a positive or negative, okay? And they have an absolute value. So positive means this is a positive word, such as good. And a negative value means this is a negative word, such as bad, okay? And the absolute value of disaster could be larger than for bad, okay? And the absolute value for fantastic, okay, can be larger than that for good, okay? So that's the idea of a sentiment lexicon. So if you know the sentiment value of every word, okay, then you can do sentiment analysis by just summing up all the sentiment words in a document as the sentiment value of the document. The basic idea is if the document contains a lot of good words, then it's a positive. It carries a positive sentiment, okay? Otherwise, it carries negative sentiment. But you'll say, no, all right? There is still negation, right? And there is sarcasm. Okay, it turns out that these are factors, but this very simple method works extremely well, okay? It remained a very strong baseline for a long time. Okay, and it is used, okay, for stock market prediction for a long time, okay? So if I use this for sentiment analysis, then the first thing is, how do we build this sentiment lexicon? All right, so now the people use the higher linguist, okay, to score a word. Okay, good is 1. Fantastic is 3. Okay, bad is -1. Disastrous is -3. But it turns out that people cannot agree on the values, right? It's quite tricky to label all these sentiment words. And so PMI can be used to help us, okay? What I mean, so suppose we're doing tweet sentiment analysis, okay? You know, you have a lot of tweet messages. Some of them are with this smiley, others are with that smiley, okay? Say, I scored 100. You must write this smiley, right? So I scored 55. Okay, probably this one, okay? So I say, if I count, okay, which words normally co-occur with this one, okay? There could be good words, right? Which words co-occur with that one, bad words? But you also note that, okay, words like the and I, okay, they can co-occur with everything. So I want to like diminish the influence of that, okay? And PMI is exactly what we need, okay? So if 2 words co-occur together in a tweet, then the probability of the joint event is high, okay? How do I calculate the probability of joint event? By calculating relative frequencies, right? then divide it by the probability of every word. So this is the PMI between a word and a seed. And the sentiment polarity, the sentiment score of a word can just be the PMI between the word with a good smiley minus the PMI of the word with a bad smiley. Okay? So that turns out to be very useful for mining sentiment lexicon. Let me give you a second example. So, collocation is a linguistic term. So when two words are frequently used together to mean something, it's a collocation. For example, I can say Mr. President, okay? So that's a collocation. But I don't normally say Mr. Executive, okay? So similarly, I can say high temperature, okay? But I don't normally say large temperature. That's a collocation, all right? So how do you know that when two words are together, it's a collocation or not? Again, we can use PMI. And this time, when I calculate the joint event, I calculate the probability of a bigram when two words are together, okay? You know how to calculate bigram frequencies, but this time it's not a conditional probability of next word given the first word. This time it's just the relative frequency of bigram over the number of all bigrams, okay? And divided by the probability of each word. That's PMI. And we know high PMI bigrams are normally collocations, okay? The third use, as I said, is features. You know we define the feature vector, right? The feature vector contains the number of words and a class label. And you'll also learn stop words, you know? When I have the feature templates W and C, I extract a long feature vector, okay, with every composition of word and class labels. But the stop words are also in it, you know? In for sport, in for technology, in for politics, in for finance. But this doesn't make sense, right? Maybe in your data, in co-occurs more in the sport news, but it doesn't mean that in and the sport is an indicative feature. It's called a spurious feature. It's just noise. If you rely on that feature, your model cannot generalize very well, can overfit your training data. So, can we filter our feature vector by deleting those feature instances that contain stop words and not so meaningful word class combinations? Again, we can use PMI. We can calculate the PMI values between the feature instance and the class label, okay? And for those not so indicative features, we can remove them, which makes our model faster and maybe free of spurious features, okay? So faster and more accurate. Okay, so now we are ready to discuss the representation of words. So we used to turn documents into vectors, okay? Count-based vectors, TF-IDF vectors. Can we turn words into a vector? Of course. The most simple, okay, and intuitive method is to turn a word into a vocabulary size vector, where only the dimension that corresponds to this word is 1, right? And the other dimensions are zeros. This is an indicative feature vector. It's called a one-hot feature vector. Okay. Among V dimensions, only one is 1, and the remaining are zeros. And this vector can be useful. Okay, at least it can differentiate different words. But it does not tell you the similarity between words, because when you calculate the distance between any two words, okay, it's the same, right? if you calculate the cosine between any two words, it's 0. Okay, so I cannot tell you that cat is similar to dog based on these vectors. So how can I solve this problem? Okay, there is a famous hypothesis called distributional hypothesis. And I can also translate that into a sentence. You know the meaning of a word by its neighbors. Okay, so I give you an example. So cats and dogs, they are also always mentioned together with something like run, okay, jump, right, eat, fur, legs, what else? Head, right? So these words always co-occur with these other words. But when you think about cat and car, okay, maybe their co-occurring words are less than those between cat and dog. So can we use the distributional hypothesis to represent words? All right, so this is the idea. So whenever I have a word, okay, and I have a corpus, then I can define a k-word window. So maybe I look at k-words on its left and k-words on its right, okay? I have a sliding window. Okay, no, not a sliding window. I have a k-word window around this word. I can do that, right? So for every occurrence of the word, I accumulate its neighbor counts into a vocabulary size vector, okay? So as I show you in this example, when k is 2, I look at 2 words on the left and 2 words on the right. When k is 5, I look at 5 words on the left and 5 words on the right, okay? And I showed you the k-word context of the word bank in these 2 sentences when k varies. But this is easy to understand, okay? So when I have a corpus, I just accumulate the count of every word, okay, in a k-word window to a current word, to represent the current word. As a result, all right, I get the context-based vector for cat and dog. Okay. So maybe F121 means cat, F500 means dog, and F1 means what? Means right? Is the first word in the vocabulary, and maybe F35 means run, okay? Ran, the past tense. So you will see that when you use the word count in the context to represent the 2 words, cat and dog can be similar. Can be similar because their co-occurring words are similar. But then you found the problem. What is the problem? The problem is that the stop words, they co-occur frequently with every word, right? Which makes every word similar to other words. So this is not desirable. Okay, so I can change the count into a PMI, okay? I can just use the PMI between a context word and a current word to represent the context word bit, the context word element, okay? So where PMI, the joint probability is the probability of the 2 words co-occurring in a k-word window, right? And the probability of a word is just the relative frequency of the words. So you know, stop words, they have high values in the joint probability, but they also have high values in their own probabilities. So their relative value will be smaller in a PMI vector. And this is a result. You will see that the first word, okay, it used to be 1,000. Now it's changed to about 1 or less than 1, which makes the vector more indicative. So this is a better word representation, okay? Now we can calculate the similarities. And as I mentioned to you earlier, PMI can be negative, okay? If two words, they separately co-occur more frequently than their co-occurrence, if two words, they separately occur, right, more than their co-occurrences, their PMI is negative. But which is not so useful when I define a word vector. So we can set all negative PMI to 0, resulting in a positive PMI or PPMI value. So we can use PPMI in the word vector as a word representation so that every element is non-negative. Now it's time to make a summary, okay? So what did we review today? We reviewed information theory, okay? The first part, we reviewed information and entropy, and I showed you something very impressive. I can use the maximum entropy principle to build a model. And when it is a feature-based probability model, it's a log linear model with MLE, okay? In the second part, I showed you how to use information theoretical measures to measure two distributions, right? The first is about two distributions of the same random variable. Cross entropy, model perplexity, KL divergence, okay? And these are useful for measuring the difference between a model distribution and the empirical distribution, or the data distribution. And that is useful for model training and model evaluation. We showed both cases. And the third part, I showed you mutual information. And especially, I showed you how to use PMI, pointwise mutual information, to do text mining and to represent words. Okay? So that's it for this week.